Welcome back, everybody. In today's video, we're going to be looking at the parts of our basic manual wind movement and looking at the different tolerances of what they should look like. If this sounds like something you'd be interested in, let's get started. In my opinion, one of the biggest mistakes that people make when they get into watch repair is to start off trying to fix a vintage watch movement. I don't care what it is that you're trying to fix. If you don't know how things are supposed to operate, how things are supposed to look, then how in the world are you going to be able to fix something if you don't know what it's supposed to look like? The tolerances between watch parts is so minimal, there's no way to physically measure them. There's no way to get a tool inside to measure to see if things are right or wrong. This is something that you have to learn by looking at. You have to develop the eye to be able to look at a wheel, for example, to see if there's too much end shake in it. When you start off trying to repair vintage watches, you have no idea if the parts inside the watch are correct for that watch movement. You have no idea how many hands have touched and tried to repair that watch. So today, we're going to look at a new watch movement. We're going to start developing a feel for the tolerances that parts should have so that you know what to look for when you finally get into trying to actually fix a vintage watch. Let's go ahead and we'll just jump right in. When you start servicing vintage watches, you're going to go through a process of inspection while you're disassembling the movement. In order to know what's right or wrong, you need a reference for what's right. Unfortunately, there's no way to physically measure for these tolerances, so your only point of reference will be a visual reference. The exception to this rule is on the dial side with the keyless works and the motion works. Your point of reference on this side of the movement will be your feel and touch. Get a feel for how much resistance there is between the stem and the mainspring as you wind the watch. Feel how the yoke jumper and the setting lever interact with each other when you pull the stem out to the second position. You can feel these two pieces interacting with each other. Now pull the stem out to the hand winding position and feel for the friction between the cannon pinion and the extended arbor. Get a sense for how much resistance the cannon pinion needs to be able to turn the hands. So let's go ahead and let the power down and we'll start disassembling the movement. So just holding the click back, we gently let the crown slip through our fingers until all the power has been released from the mainspring. Now we can remove the arrow wheel, the setting lever jumper, the yoke spring, and the yoke. So looking at the minute wheel, just checking the wheel for flatness seems pretty self-explanatory, but the main thing that you want to get used to seeing is the shape of the teeth. The more you study the shape of the teeth and what they should look like under normal circumstances will make it a lot easier for you in the future to be able to identify a tooth that's gone bad or even a pinion leaf. So now we can remove the crown, the ratchet wheel, and the click spring and move on to the balance wheel. The balance wheel in a clean watch with straight, undamaged pivots will oscillate approximately 25 to 30 seconds on its own with no power to the mainspring. It doesn't matter if the watch is 100 years old or 10 years old, the balance wheel should oscillate for an extended period of time on its own if everything is in order. Now look at your balance wheel and start the oscillation with your puffer. Look how a balance wheel that's running flat looks like. Now the little up and down that you see, that is just the end shake of the air moving the balance wheel up and down. But you'll notice there's no ridges, there's no humps. It's running perfectly flat. That's exactly what you want to see. To check the end shake on wheels, I like to just use an old oiler. They're soft enough and bend enough where you're not going to risk damaging the wheel. Now, the balance wheel in particular is a little hard to get inside and look at the actual pivot. So just look at the end shake by moving the wheel up and down to see what kind of motion there should be. So now study the hairspring from the top view looking down onto the balance before we take it out. What you're really looking for is even spacing between all the coils of the hairspring. You don't really want to see any bunching up on one side or the other. That could be indicative of either a problem with the terminal curve or the regulator pins are causing it to be pulled in one direction or the other. Now look at what a flat balance spring should look like. You don't see any humps up or down, and you see equal spacing between the hairspring and the underside of the balance bridge. Now let's take the balance bridge off and we'll look at the underside of the balance wheel. One area in particular that's prone to damage is the balance wheel pivots. Get a feel for the length of a pivot and how polished the pivot should look in a normal balance staff. Notice how the bottom of the pivot is not mushroom out. Now they do have a slight rounded tip on them, but you shouldn't see a mushroomed out tip on the bottom of the pivot. Now look at the impulse jewel. The impulse jewel should be straight up and down with all the edges clean and crisp with no chips. Now looking at the hairspring from underneath, you can see the nice even spacing between the coils and how the terminal curve going between the regulator pins is nice and even. Now look at your pallet fork and get a sense of what the end shake should look like. You can lightly grab the arm of the pallet fork, gently lifting it up and down. The one area of a watch that'll kick most new watchmakers' asses the hardest is the mainspring barrel. Mainspring barrels in vintage watches are notoriously over-lubricated, and this excessive oil attracts dirt and grime, which get in between the pivot and the arbor holes in the bridge in the plate. The steel arbor turning under torque and a soft brass main plate mixed with old lubricants, dirt, and grime cause the pivot holes to become egg-shaped, allowing the mainspring barrel to start dragging either on the main plate or on the underside of the barrel bridge. The lack of wear marks on the bridge or main plate doesn't mean that everything is hunky-dory with the mainspring barrel. For maximum amplitude, the barrel still needs to be running true in the arbor holes, so you still need to have a visual reference on how much end shake a mainspring barrel needs. So here we're looking at the end shake on the ST36. What you're really trying to judge is how much clearance the barrel has between the bridge. Now, as we go through these series of videos, we're going to be diving deep into the subject of amplitude. Amplitude is extremely important to the timekeeping of the watch, and it is the one area that new watchmakers struggle with because there's so many things that can affect the amplitude. From the mainspring to the pivots of the mainspring arbor to the end shake of the arbor between the barrel drum and the barrel lid to the train of wheels. I mean, it goes on and on. So we'll be getting into that much deeper in some of the upcoming videos. Now, as we move on to the train of wheels, one of the things that's important to realize is that, you're looking at end shake through a microscope right now, and your visual reference may be through a 10 or 15 times loop. So you have to kind of figure out how you're going to be doing your inspections, what you're going to be doing your inspections with, and start looking at these tolerances the same way all the time. Now, one of the things that you're looking for when you're looking at your end shake in the train of wheels is you're looking for consistency. So you're looking for very small movements, and what you're trying to train your eye to be able to differentiate is one wheel that's moving more than the other wheel. So now when we check the end shake of our third wheel pivot, just again using an oiler or a probe, you can clearly see how much it's going up and down in the pivots. So I can almost hear you asking, Alex, how do these jewels get out of place? Why would the end shake be different on wheels? Well, there's a couple different reasons. One, when you're installing hands on a cannon pinion, oftentimes if too much pressure is applied, those jewels can actually get moved from the force of pushing down on the hands. The other reason is somebody has replaced the jewel and they didn't adjust it properly. One of the main reasons that it's important to know the way things should be is because when you start dealing with vintage watches, you're going to run across all kinds of things. You can never assume that anything is correct, and it's your job as a watchmaker to identify what the problems are so that you can fix it. Before you know what's wrong, you have to know what's right. Now let's get to that bonus tip. Determining the correct condition of a watch jewel is one of the easier things to do. With a watch jewel, it's either broken or it's not broken. It's either cracked or it's not cracked. But you have to be able to get in close, and you need to be able to look at it clearly. The easiest way that I have found to do that is by simply laying the bridge on a couple pieces of pegwood and then shine a flashlight under it. It'll illuminate the jewel from the underside, and if there's any cracks or chips in the jewel itself, you'll be able to see them right away. Well guys, that's it for today's video. I hope you got a little something out of it. If you have any questions or comments or video suggestions, please drop them into the comment area. And as always, if you want to support what we're doing here and you learned something, give us a thumbs up, and that way it'll help get the message out. Until next time, my friends, we're out of here.